Let us do the case third of closest distance of approach between two charged particles. Now this case is a little bit different. So before discussing this case, let us understand what impact parameter is. Now impact parameter is nothing but the distance between the charged particle, a moving charged particle, suppose Q2, up to which it goes to another charged particle, suppose Q1, and they are not in a straight line. This is the straight line for Q1 and Q2 is going like this. Now since charge Q1 is a positive charge, so it will have some electric field. Now when Q2 approaches Q1 in this way, then after a point it will face the repulsion and will go like this. This area or this distance at which Q2 faces repulsion is called impact parameter. Okay, so it is a little bit different from distance of closest approach because the two charges are not in a straight line. So in this case the impact parameter and closest distance approach are two different things. If Q2 and Q1 are in the same line, in a straight line, then impact parameter and distance of closest approach are one and the same thing as far as numericals are concerned. So let us do this. Suppose we have charge Q1 which is fixed here in this position, and another charge Q2 at a distance of d. Now here impact parameter is d. Let this Q2 charge is moving in this direction with a velocity v0 and has mass m. Now as it moves, the trajectory of this charged particle will be like this because of the repulsion. So now the distance of closest approach will be a line joining Q1 with this trajectory, and this should be the shortest line. Now if this is the shortest line, then it will be perpendicular to the trajectory of Q2 because we know that the shortest distance is the straight line, so it will be perpendicular. So this distance will be r0, that is the closest distance approach, and let's say that after this the velocity of charge Q2 is v. Now since the trajectory is not a straight line, it is curving at this point, so we cannot apply conservation of linear momentum here. There is no linear momentum, it is not a linear motion, it is a two-dimensional motion. So here we will apply conservation of angular momentum. So according to this, initial angular momentum m v naught d will be equal to final angular momentum m v r naught. From this we will get v equals to v naught d, the v is the final velocity, v equals to v naught d upon r naught. Now by applying conservation of energy, initial energy equals to final energy, so initial energy when Q2 was away from Q1 was only kinetic energy, so it will be half m v naught square equals to final energy. Final energy is the combination of kinetic energy, that is half mv square, and the interaction energy or the potential energy between Q1 and Q2, which is given as k Q1 Q2 upon R naught. Now if we put the value of v from the last equation, from this equation here, then we will get the equation half m v naught square equals to half m v naught d upon r naught square plus k q1 q2 upon r naught. Now we have to solve this equation for r naught. Okay, if we solve this equation, the easiest method is to convert this equation, rearrange the terms and get a quadratic equation. Now when we do that, the quadratic equation that we will get will be mv naught r square r naught square minus 2k q1 q2 r naught minus m v naught square d square equals to 0. So this is the quadratic equation that we need to solve or to get the value of r naught. Now the easier method will be to not solve this quadratic equation by using quadratic equation, but keep it as it is. Either you learn it just like this or do not learn it at all. The most important thing is the concept. If you understand the concept of all three cases, then you do not need to learn by heart any of the formula. Okay, so from this we know, if suppose a numerical is given on this case, then we will have all these values and we will put them in equation and we'll get a resultant quadratic equation in the terms of r naught, and then you can find the square roots.